Okay, in this video we're going to talk about ciphers. I kind of made this video for you folks that are actually doing cryptography for your IAs. So this is a video. This is going to be a video on the Hill cipher, which is a type of block cipher. Call that here Hill cipher. Okay, so we're going to talk about why the Hill cipher would be used and the weaknesses of the other ciphers that you could possibly use. So in other ciphers you could use, like the shift cipher, the affine cipher, substitution cipher, all these different types of ciphers. Okay, the weakness for them, okay, is a given letter in the ciphertext always comes from exactly one letter in the plain text. Okay, so how cryptography works is we're going to take a plain text message, which is our message we want to send to somebody, and we will encrypt it. Okay, and we'll encrypt it here into what is called a ciphertext. And then the idea is to decrypt it back into the plain text somewhere else. Okay, so as a message is being passed from A to B, it has to be encrypted. So this is the encryption part, which is usually the easy part, and this is the decryption part. Okay, and the thing is, this plain text could be just some word, I mean anything message, like the word dog, for instance, right? And for every character in this plain text message, it's dependent on, well, every character in the ciphertext message is dependent on one character for the plain text. Okay, and that's what's true for these. So basically, these are weak because they are subject to frequency analysis. They can be attacked this way. And you need to look up what frequency analysis means. It's basically they're looking at all the letters of the alphabet, and technically if you've actually typed a paragraph, some letters will appear more often than others. This is just a natural thing for the English language. So what they can do is they can look at a long message and then look at the frequencies of commonly used letters in the English language, and they can actually use it to figure out what this was. They can decrypt this message from this, called frequency analysis. It's a type of attack. Okay, but the block cipher, what we're talking about, which is the example we're using as a Hill cipher, this isn't so. Okay, the ciphertext doesn't translate directly to one letter on the plain text. In fact, if you change one letter of the plain text, it'll change all the letters of the ciphertext. This one, if you change one letter of the plain text, it only changes one letter for the ciphertext for all three of these. But for the Hill cipher, if you change just one, it'll change actually all the terms or letters or numbers or whatever for the ciphertext. So it'll change all of them. Okay, so this is great. It's not a one-to-one relationship. So anyway, if that makes any sense to you, and you'll see here kind of what I'm talking about. So we're gonna let's just use this word actually as my plain text. This is gonna be my plain text, and we'll convert it. So we have the alphabet here assigned to numbers, starting at 0 for A, 25 for Z, and everything in between. So I'm going to actually convert the word dog into a numerical format. So D is going to be a 3, O is going to be a 14, and G is going to be a 6. Okay, and so this is right here. This is my plain text. Okay, this is the numerical form. This is the text form. Okay, and what I'm going to do is I'm going to think of a number that's bigger than 1 called n. Okay, and whatever n is, the key that I'm going to use to encrypt it, there's a key which I'll call K. To make the ciphertext, it's going to be a matrix. It's going to be an n by n matrix for the Hill cipher. Okay, in this case, in this example, I'm going to say n is equal to 3. So I'm looking at a 3 by 3 for this example. Okay, so that's my key is a 3 by 3 matrix, and my key, I'll call it K. That's my key. Okay, and once I get the ciphertext out of that, I will decrypt it using the inverse matrix, the inverse of K. Okay, so this is my key. This is the inverse key to decrypt it. Okay, so if I were to change just one of these characters after, from the encryption, it'll actually change every character in the ciphertext. So this is 3 characters, the ciphertext will be 3 characters, but the deal is, if I were to just change one here, it would change all 3 of them here. For these 3 up here, if I were to change one character, it would only change one character, and the rest would still be the same, corresponding to this. So this is why this is actually more useful or more robust and harder to decrypt or to attack using frequency analysis. So in fact, it's not really feasible at all to do frequency analysis, but that doesn't mean it can't be attacked. There's other ways to attack things. But anyway, let's talk about how to encrypt this. This is the easy part. I'm just giving you a little overview. So the encryption part. Okay, so here's what I'm going to do. My 3x3 matrix, I'm just going to make up a key. It's going to be a 3x3 matrix, and I'm just going to make one up. Okay, well, I'm not really making it up per se, because technically there's got to be a property to it that has to be true, and we'll explain that in a second. But the key I'm going to use is 1, 2, 3, 4, 5, 6, 11, 9, and 8. And you technically could find a bunch of keys that work on the internet. Just randomly pick one. Anyone would do if you're doing an example problem on an IA. But this is the one I'm going to use. 1, 2, 3, 4, 5, 6, 11, 9, and 8. And here's what has to be true. When I take the determinant of this matrix, which is the key, this is K, which is the key, the greatest common divisor of that determinant of K, which is just some sort of scalar, and the number 26 corresponding to the alphabet, because we're going to do mod 26 for this, has to equal 1. This must be true to use the Hill cipher, because if this is not true, then you can't actually find the inverse of that matrix. The inverse wouldn't exist. So that problem means you wouldn't be able to decrypt the message. So this has to be true for your key. Okay, the determinant of your key has and 26, the greatest common divisor, which is the same thing as the greatest common factor, needs to be 1. Okay, that's the only rule. But this one, it'll work, and you can find a bunch of other examples that'll work without using this one. So if you were going to do such a thing. So anyway, that's a lot of long-winded explanation, but I'm going to encrypt this message. So if you have the patience to watch all this, cool. All right, so the message I have here is 3, 14, and 6. And that means the word dog. So here's the deal. N is the number I chose, which gives me a 3x3 matrix. Your block, this is called the block, needs to be of size n. So this is of size n, the block. So this is a block of letters, okay? So this is going to be 3, 14, and 6. That's the size of my block. If I were to say n is 4, I would need a 4x4 matrix, and guess what? I could have a block of 4. But that's not what I'm going to do. I just have one message, block of 3, and I'm going to multiply. I'm going to use the plain text and multiply it by the matrix K. The matrix K right here is this matrix. So I'm going to multiply it. Matrix multiplication like you learned in Algebra 2, or should have learned in Algebra 2, making that presumption. So this is actually not hard. It's all algebra. So the matrix multiplication, this is a 1x3, 1 row, 3 columns, and this is a 3x3. Something you should check before you ever multiply a matrix or 2 matrices is that the number of columns of the first one is the same as the number of rows in the second. If this is not true, you can't multiply them. It wouldn't be possible to get an answer. But it is true in this case. And the answer is another matrix that'll follow this. It'll be a 1x3. That answer is going to be a 1x3. A 1x3 matrix. So how do you find that 1x3 matrix? Well, it's easy. I'm going to do it down here. And actually, I don't even make it that big. This is fine. So here's what I'm going to do. I'm going to take the entire row here and multiply it across the column. Like this. We're going to use a dot product. So it's going to be 3 times 1. That's exactly what it is. It's a dot product from vectors. Plus 14 times 4. Plus 6 times 11. We'll do this again. This row over this column. Now, so it'll be 3 times 2. Plus 14 times 5. Plus 6 times 9. Plus 6 times 9. And then we got 13 times 3. So we're going to do this one more time. I'm sorry, 3 times 3, not 13. 3 times 3 plus 14 times 6 plus 6 times 8. And I got this, okay? So we're going to go ahead and figure out what these are. I'm going to go ahead and just rush through that. Okay, so when I solved all this out, it gave me this right here, this matrix here, which is a 1 by 3 matrix, as I promised. It's a 1 by 3 matrix, okay? And what we're going to do here is we're going to mod this 26, modulo 26. And a modulus is really just a remainder. And I'm going to show you a good way of doing this. There's an algorithm to it, of course. And what I'm going to say is n is equal to, this is how you convert a number mod 26, is equal to q times m. M is the modulus. In this case, m would be 26 plus r. Okay, so this 26 is your m value. Whatever mod you're taking, it doesn't have to be mod 26 for all cases, but since this is the English alphabet, this is going to be 26 characters. So this is what we're doing, because we're translating a message that is in the English alphabet. So this right here, n is going to be this number right here. So n is going to be, in this case, 125. We'll convert 125 mod 26. So what I have here, this is q times 26, we're multiplying this, plus a remainder. This remainder is the mod you're trying to find. So here's what I'm going to do. I need to make sure that this quantity is less than this. So I have to figure out what times 26 would give me a number that's just underneath this one, close as I can get to it without going over it, right? So here's what I'll do. I'll take 125 and divide it by 26. Okay, so I get a calculator, and I'll take 125 and divide it by 26. And it gives me 4.8. So I'll go ahead and multiply the integer part, not the decimal, but the 4, times 26, which is 104, and then I'll take that away from the 125 I started with. So it means I have 125 minus 104, which is 21. So here's what this means. Okay, this means 125. This is going to be 4 times 26 is what I said, right? Plus r. And what I had here was 104 plus r. Okay, so 104 plus the remainder gives me 125, and that remainder is going to be 21, is what I'm saying. So this is how you actually mod the number. I'm going to say that 25 right here, 125, sorry, is congruent. Okay, congruent or the same as 21 mod 26. This is what that means. Okay, this is how we say it in cryptography. So you have to understand modular arithmetic to actually do cryptography particularly well. And I'll post some videos on how to do these conversions. But this is actually kind of cool thing. But you can do this with the rest of these, and I'll go ahead and do it for you so you don't have to see it. So I'll rush through that. Okay, so here are my remainders. So what this means is that this is equal, when it's modded 26, is going to give me 21, 0, and 11. This is called my ciphertext. I have encrypted this message. And this ciphertext corresponds to 21, which is V, 0, which is A, and 11, which is L. So this course, if you were to give the message, is val. So the initial word was dog, if you remember, dog. And this is the plain text, and this is the ciphertext. We converted the word dog into this word val. So somebody that picked up your message after you encrypted it, they're just going to read the word val. It's not a word, doesn't make any sense. They don't know what the original message was. It's encrypted. So that's the encryption process, okay? The decryption process is significantly more involved. Encryption is actually pretty easy. And I just did it right here in a couple of steps. It only takes a few minutes, just this page of work right here. But the decryption is the hard part. So if you want to keep watching, go for it, and I'll show you how to decrypt this. And then this is maybe something you might want to try to consider. There's a 2 by 2 matrix you could do with this. It's a little simpler. significantly simpler actually. But the 3x3 is really cool, and it took me a while to learn how to do this because I had to learn it myself. But after you watch about, I don't know, 10 YouTube videos and read a book or a couple pages out of a book, you can figure out how to do this. Pay close attention. This is the decryption. Okay. And the decryption is going to work this way. We're going to change the ciphertext back to the plain text. And this is going to be a little involved. Okay, so here's the deal. What we're really doing is we're taking the plain text, well, the ciphertext, which is a matrix. Okay, we're going to take that ciphertext matrix right here. And how did we get the ciphertext anyway? The ciphertext, we'll call it the cipher matrix, is equal to the plain text matrix times the key matrix mod 26, like this. Okay, so the cipher, if I multiply it by the inverse, we say key, I should say K instead of key. Let me fix that, because I'm going to keep using K in my notations here. K means key, by the way. So multiply this by the matrix K, which is your key, and it gets this. So if I multiply the cipher by the inverse matrix of the key, this should equal, and I do this mod 26. I don't forget that. So important is the mod 26. That's actually one of the harder parts of this. Mod 26. Okay, this would equal your plain text. But how do you get the inverse? Okay, this is actually not easy. Okay, so the inverse is equal to 1 over the determinant of the key, times the adjunct matrix of K. So there's some vocabulary you're going to have to figure out here and define if you were going to use a cipher like this. You would have to obviously define what plain text and ciphertext means. You would have to define what a determinant is. You have to define what an adjunct matrix is. And I'll briefly describe kind of what an adjunct matrix is. And to describe that, you're going to have to use what is called a cofactor matrix. And some terms here that are going on here, okay? And then you're going to have to figure out, another thing you have to know how to do, put on some terms here, is a greatest common divisor, or GCD. These are all things that are going to come into play in this process. Okay, so let's go through it. I'm going to try to walk you through it the best I can. All right, because I'll be honest with you, it was fun figuring this out. All right, so the trick here, so this is 17, 0, and 11, and the trick here is finding this guy. That's the hard part. Okay. So here's what I know. Let me talk about the inverse really quick. The inverse of a matrix, if you were to multiply, so we'll talk about inverse for a sec. Inverse matrix. If you were to multiply the matrix K times its inverse, what you would get is the matrix I, which is called the identity matrix. This is kind of how you represent the number 1 in a matrix. So this is called the identity matrix. Identity. Oops, there's not a D there. And if you've taken Algebra 2, you should have learned some of this. And hopefully you've learned this in Algebra 2. And the identity matrix for a 3x3 would look something like this. I'm just going to sketch it here. It would look like 3 1s here and a bunch of zeros all around it. So you get a 0 here, you get a 0 here, and 2 zeros here, and look like that. Okay, so just 1's going across the diagonal. Okay, but That's all great and stuff, and there's a couple ways you can learn how to do that or figure out how to do that. But in order to explain all that's going on, we're going to do it a very specific way to find this inverse. Okay, so I'm going to use actually this formula to find this inverse. So what I'm going to do first is let's find the adjugate matrix first. Okay, I'm going to do that first, and then because this is going to require some explanation, this determinant mess here. Okay, so the adjugate matrix. So the adjugate matrix is really the transpose of the cofactor. So the adjugate of K, adjugate matrix, is the transpose. So if you recall, my key was this. I'm just throwing it up here on your screen really quick. That's the key I used right here to encrypt this message from the beginning. Okay, and what I have to do now is find the cofactor matrix, and this is the transpose of the cofactor matrix. So we'll do this first, and this requires determinants in of itself. Okay, so let me use my bars here. So to show you how to find cofactors, I'm going to use these bars that I've made here, and this is what we're going to do. Okay, we are going to find my cofactor matrix. We'll write it like this: cofactor matrix, this way. So we're creating a matrix of determinants is really what this is. So here's what a cofactor, how you find a cofactor. I'm going to cover up the first column and the top row, and anything that I haven't highlighted in blue here is what's going to get written in the determinant. So I'm going to have 9 different determinants or cofactors. Okay, these are called cofactors, and what I'm going to do here is anything I didn't cover up, so I'm covering up this first column, first row. These 4 numbers go in here. It's going to be 5, 6, 9, and 8. And what this really is a determinant of a 2x2 matrix, which is really simple to do. Okay, and all I'm going to do now is I'm going to move the column. So this column now will get moved. Oop, I don't want the numbers to move. I want to move the column here. So the numbers I haven't covered are now 4, 6, 11, and 8. Okay, so we just keep sliding the column over. So what I'm going to have here is write this down. Keep changing my markers. Okay, we got 4, 6, 11, and 8. Okay, and we do it again. And there's a formula for this, of course, that you can find. So there's, there's formulas you can use to explain what you're doing, which is great. And then we got 4, 5, 11, and 9. But I didn't search for them. It's bad enough I'm trying to do all this. Okay, so now what I'm going to do is I'm going to move this row, this column, this blue column back, and I'm going to slide this thing, the row column, down by 1. So now I'm going to do this process again. I'm just going to keep sliding the column to the right and do this whole process again from here. And whatever numbers I haven't covered up, they get written into these cofactors. So what I have here is I have 2, 3, 9, and 8. So you would have to look up all these words I've written over here and explain what they are if you're using this process. If you're not using this process, then you don't have to do that, right? So it's fine, but it's your IA. That's the thing. This is just me trying to help you out, showing you something that's possible. And I'm going to, and there's others probably I'll try to do for you, or to show you how to do as well. But I had to learn this myself to help you. So I got 1, 3, 11, and 8. And then I'm going to copy this over, move this over. And then I'm going to write this down, which is going to be 1, 2. And I know this is kind of tedious and boring. Thank you for bearing with me. And then now we're going to do this one more time. We're going to move the column back and then move the row down one more. And then we're going to do this one more time all the way across. Keep sliding that column across. So here I got 2, 3, 5, and 6. And this isn't really the cofactor matrix yet. We're going to it. So we need to put an arrow, not an equal sign. So right here, I'll show you what I'm talking about, what I'm missing here. It's going to be, the signs are important, is what I'm going to be missing. Okay. So here, I'm going to I'm going to move this column down, move this column over like this, and I got 1, 3, 4, and 6. And 6. And the reason this takes so long is because this pen is not easy to write with. And if this video goes awry, I'll try to do it on my iPad, because it's a lot easier to write on an iPad than this tablet I'm using. So I got 1, 2, 4, and 5. Okay, so the cofactor matrix, here's the tricky part with the cofactor matrix. Let's actually do these first, actually, and show you. These are determinants. So how you find this determinant here, and we're going to use up all the space we have, is I'm going to do 5 times 8. We're going to do this times this minus this times this. So it's crisscross. It's left down to right multiplied minus bottom left times top right. So this is really like 40, right? Minus 54. That's what that is, okay? 40, this times this, minus this times that. That's really what I have here. We're going to keep doing this. It's going to be 4 times 8, right, which is 32, minus 66. 4 times 9, which is 36, minus 55, because it's 11 times 5. And then right here, we're going to do this time minus this times this minus that times that. We're just going to keep doing this process over and over. It's going to be 16 minus 27. I'm going to get 8 minus 33. I got 9 minus 22. I got 12 minus 15. I got 6 minus 12. And this process here, as you can tell, is not for someone who doesn't have any patience, okay? And there's a lot of people out there that don't. We're just not capable of going through all this. So here we go. 1 times 5. But code breakers definitely do. 5, and then subtract this, minus 8. It's all about patience. Sometimes it could take years just to learn how to crack one code. That's what it, back in the old days. And the Enigma code, right? And Alan Turing and all these people, right? So you've heard about them. Alright, so this right here is what I have here, and here's how the cofactor matrix needs to be set up. The signs are extremely important, and this is and if you do this wrong, this is going to be bad. So this will go plus, minus, plus. So once you start with plus, you just keep alternating and keep going through the rows. So it's going to be minus, plus, minus, and then you're going to have plus, minus, plus. The signs need to be like this. So what I'm basically saying is you can put this in parentheses and put a sign in front of it. You can put this in parentheses and put this negative in front of it. This negative right here. And this right here would be a positive and so forth. So this must happen. If you do this, if you skip this or you forget to do this, then everything is going to go awry. Because the cofactor has to have these signs. Cofactor matrix has to have these signs. So this is the important part. So that's just plus. This will be minus. And this will be plus. Okay? And don't forget to do that. Okay, so here's what I'm going to do. What this is going to give me is here I would have a negative 14, but there's a plus in front of it, so we're going to keep it that is negative 14. It's plus times negative 14. Here I have, what I have here, I got 34, yeah. So this is negative 34 with a negative in front of it, so it's actually going to become a positive 34. Okay, so it's really important you utilize the negatives when you see them. So I got 36 minus 55. Let's see, what is that? 15, is it 19, I guess? So negative 19 right there. Okay. And what do I have here? I got, what is that, a negative 11? Yeah, negative 11. And then there's a negative in front of it, so it's going to be positive 11. And then here, what do I have? 33, it's 20, negative 25. And then there's a positive in front of it, so it stays negative 25. And if I make any mistake here, then the whole thing is going to go bad. That's the problem. So you just must be very careful. So I have here 22, so that's going to be negative 13 times a negative, which is a positive 13. Difference right there. And then here I got a -3. And then here I got a -6 times a negative, which is a +6 is what's going to happen. And then here I got a -3 just by itself. And this right here is my cofactor matrix. This is actually what it is, cofactor matrix. And now what I got to do is find its transpose, which is called the adjutant matrix. And this is actually not that hard. The adjutant matrix. So this is the cofactor matrix of K, and this will be the adjutant matrix of K. And here's what you do to make the adjutant matrix. It's really simple. There's some properties here. We're going to look at the diagonal, these numbers right here in diagonal. We're going to copy them over. And then what we're going to do here is kind of treat this diagonal. Let's actually highlight that maybe, or encircle it, or whatever I can do. And we're going to take the other numbers here, and flip them across this line. So this 11 will go where the 34 is, and this 34 will go where the 11 is. So this will be 34, and we're transposing these. So this is the transpose of this matrix, and this will be 11. And then -9. Right here we'll flip this with -19 rather. We'll flip it with -3. So this will be -19 down here at the bottom, and -3 up here at the top. And we'll flip the 6 and the 13. So this 13 will go here, and the 6 will go here. So this is how you find the adjutant matrix. Okay, so you have to kind of do some research and explain what that is as you're doing it, and explain the process if you follow this process, right? Assuming you do. Okay, so got it. Now what? What did I just do? Well, I've just found this. But now I have to find the determinant and then find its inverse. This is 1 over the determinant, which is called the inverse determinant. Finding the determinant is actually not that bad. Finding the inverse of the determinant is the hard part. Okay, so the determinant itself is not that bad. And there's actually 2 ways you can find a determinant. Okay, so we're taking the determinant of this matrix K again. So I'm going to move this stuff out of the way and show you. This is the matrix K. We're looking at K is everything. It's the key. Okay, so let's say somebody that's trying to decrypt your message, they found your key. They'll be able to do it if they, follow all these processes technically. So here's what I got here. All right, so this is your key. I'm going to take the determinant of the key, and there's a couple ways you can do this, and there's really a way you should do this, and the way I'm going to do this. I'm going to do this the short way. Okay. But if you were actually explaining this on a paper, you should do it the long way, right? And you can watch plenty of videos on how to do that, but this is the short way. I'm just going to kind of get through this video now, because I know I'm taking up your time. But the determinant of K, what I'm going to do is copy the matrix itself, K, which is going to be 1, 4, 11. I know I'm going back and forth here. 1, 4, 11. I'm just going to copy that matrix K. I got 2, 5, 9, 3, 6, 8. So 2, 5, 9, 3, 6, 8. And the shortest way to take a determinant, which is not really, not a lot of explanation for this, some sort of trick here, okay, but this is not really the way you should do it on an actual paper. I'm going to copy the first 2 rows, first 2 columns again, 1, 4, 11, and 2, 5, and 9. And the way you can find this determinant quickly, relatively quickly, is we will look at the diagonals of 3. We got this right here. We got this right here. We got this right here. These 3 numbers, these 3 numbers, these 3 numbers. And then we're going to look at diagonals going the other way of 3. This one, 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 this one. So one way you could take a determinant of a 3 by 3, the fastest way you could do it, is you could say these left to right diagonals in black here, we're going to multiply all these numbers. Okay? And then add. So we're going to say 1 times 5 times 8, which is 40. 1 times 5 times 8, which is 40, plus 2 times 6 times 11. So that's 66 times 2, right, which is 132, I believe. Sometimes my math gets wonky. And I got here, I got 12 times 9, right? So that's going to be 90 and 18, right, which is going to be 108. So we just added all these. So the black lines, we multiplied every number and then added them together. And then for the blue lines, we're going to subtract them all. So this is going to be 5 times 11. Actually, it's going to be 5 times 3. We'll do 15 times 11, right? So that's going to be 150 and 15, which is going to be 165. We're going to subtract 165. So it's this times this times this, and then subtracted, which is 165. And here I just got 9 times 6, which is 54. So I'll subtract 54. And then I got 8 times 4, which is 32, times 2, which is 64. We'll subtract that. And then once you find this answer from this little operation here, that's your determinant, okay? So when I figure this out, this is going to actually equal -3, okay? All right. So this is determinant is -3. So what I know now is the determinant of K is in fact -3. Now what I have to find is the inverse, okay? If I multiply the determinant of K by its inverse, it would equal 1. It's a multiplicative inverse. We're saying, okay, well, boss, that's easy because this is -3, so the multiplicative inverse of -3 is -1/3, right? And that should just equal 1, and it's done, right? Yes, but this -1/3 needs to be written mod 26. That's the hard part, okay? So this isn't sufficient. You can't just say -1/3, although technically it's numerically the same thing, but you have to mod 26 this guy. So here's what I got. So what I'm finding here, if you recall, my inverse is what I need to unlock the message of the key, is equal to 1 over the determinant of K, and this is 1 over the determinant of K right here, technically, times the adjunct matrix of K. We're trying to find that inverse to unlock it, right? So we already found the adjunct matrix, and technically we already found this, but this is not in mod 26, so we have to mod 26 this answer right here. So here's how you do this, okay? What I'm basically going to do to find the inverse, here's the hard part. It's not really a hard part. This key I use is actually really nifty because it's not as many steps. If you choose a different key, you might have to do this a little, what I'm about to do right here, a little further, okay? But what we're going to use is what is called, we're going to do the inverse modulo. And you should watch YouTube if you want to learn how to do that, because this is how I learned how to do it. And this is what I'm going to do. I am going to take this -3, and to find its inverse, what I'm trying to find is something that'll make it, well, something I'm going to multiply it by, right? What am I multiplying this -3 by here? Technically -1/3, but you can't write -1/3 mod 26. That doesn't work. So this is like something I'm multiplying it by. We call it x, and this is going to be congruent or equal to 1 mod 26, because I want this to equal 1 right here, right? Mod 26. So mod 26. Okay, so how do we do this? Well, I can divide both sides by -3, and this is like saying, okay, well, that's the same thing as -1/3 mod 26. So yeah, of course it is, right? That's what I'm trying to find. I'm trying to mod 26 this -1/3, of course. Okay, so here's how you do it. This is called the Euclidean algorithm. Well, I can't talk today. Euclidean algorithm. And then after we use the Euclidean algorithm to simplify this down, and that'll show you the greatest common divisor, then I will use the extended Euclidean algorithm to show you how to actually figure out this inverse, okay? So in my opinion, when I worked this out and figured out how to do this, this is the hardest part to me. It may not be to you actually, but it is to me because I had to stare at it and like, what are they doing? What are they doing? But I figured it out actually after a while. And here's what's happening. So what we're going to do here is we're going to take right here, we can write this a different way, but I'm going to use this -3 that I have here, okay? And this could be written, of course, you could write this way as x is what, -3 inverse mod 26 if you want to, not that it matters. But I'm going to use this -3 here, and I'm going to say, okay, the Euclidean algorithm, I'm going to copy this actually. The Euclidean algorithm, let's actually copy, let me copy this part. I should write that right here. And let me get started. I'm trying to figure out a way how to approach this so I won't confuse you too much, but here we go. So if I haven't done it already, I'm sorry if I have. Mod 26. Okay, so here's what we're going to do. The Euclidean algorithm tells me to start off by taking this mod and moving it to the very left side. So this will be 26. We're going to turn this back into its what it was before it was an inverse, which was -3. So ignoring this inverse part. And then we're going to say, okay, that's times something. And then plus something. Okay, which is like the remainder here. Okay, so if I think about that, what can I multiply -3 by and not go over 26? Okay, so I'm thinking to myself, that's probably going to be -8, because -8 times -3 is 24. So this will be 24, and then if I add 2 to it, this will give me the 26. Okay, fair enough. So here's the thing. We're trying to keep, I'll show you in a second. We're going to move, the Euclidean algorithm tells me to take this and move it over here. And then we're going to take this, which is your remainder, and move it into the place that the -3 used to be. And this is the process we keep using. Okay, so now we're going to have -3 is equal to 2 times something and then plus something else. So we keep breaking this down. And the idea is to get a 1 right here, and I'll explain to you why in a second. Okay, so let's keep doing this. So now I have 2 times what, right, to get up to -3. I could say, well, that's 2 times, I can make it more negative if I wanted to, because there's a negative here. To make it more negative, I would just simply multiply it by -2. So 2 times -2 is -4, right? And then I could add 1 to that, and that would give me what? -3. Once you get a 1 here, you can stop, right? So I chose this key nicely because technically you could keep doing these steps 4 or 5 times, and I only did it twice. But this right here is your greatest common divisor. The greatest common divisor, you've just proven, between the determinant of K, which we know is what? -3. That's the determinant of K, and 26. And it's equal to 1. This is what you've proven here, and this is actually important because if this is not true, you can't find the inverse of this number. And if you can't find the inverse of the determinant, you can't find the inverse matrix. There is no inverse matrix. And without the inverse matrix, you can't unlock the cipher text to make it make the plain text. So basically, if this is not true, the whole thing falls apart. So you need to pick a key such that the determinant of the key and 26, the greatest common divisor, which is the same thing as the greatest common factor of these two numbers, is 1. In this case, what I'm saying here is the greatest common factor between -3 and 26 is 1. If I wrote out all the factors, or greatest common divisor we call it too, of, this is 26, these numbers, the only one, so there's only 2 factors of this one. We could write this as this in 1, or we could write it as -1 and -3. But the one that we're going to use, the greatest common one to this one, which is like 1 and 26, will be 1. It's the same. And that's what needs to be true. Okay, so a little food for thought here. If you're asked, or if you're going to show that the greatest common divisor of the determinant n26 is 1, use the Euclidean algorithm. Once you finally get a 1 here, and there's nowhere else you can go on the very end, you've proven it. Okay, this is great. So, good stuff. Told you it was a little confusing. But now we actually have to, we haven't done the inverse yet, so we're going to actually have to use the extended Euclidean algorithm. A lot of math here though, which is good. Doesn't look complicated, but it's not easy actually. That's an algorithm we're using, extended Euclidean algorithm. Okay, and here's what we're going to do. Alright, so what I'm going to do now is I'm going to take this bottom number and get it by itself and set it equal to whatever's left here. So what I'm going to say is 1 is equal to -3 plus, Well, this is technically a negative 4, right? So I want to say, so I'm not going to multiply it out though. I want to leave this 1 by itself. I want to leave this 2 by itself. I'm not going to actually distribute anything. This is the tricky part. Don't distribute anything, okay? So what I have here is minus 2 times negative 2. In other words, I'm adding 4 here, right? And then this is going to be, yeah, this is it. So you agree that this is the same thing as this, I hope. Okay, so we got 1 is equal to negative 3 minus 2 times negative 2. And I'm going to do the same thing with this. I'm going to solve for the end. I'm going to solve for the end. So solve for this 2 here. I'm going to say for this equation, okay, 2 is going to equal 26, right? And this is really 3 times 8. These are both negative, so we're going to say minus 3 times 8. We have a negative times negative, which is a positive, and then we'll just subtract it from both sides. There you go, okay? So here's what I'm going to do now. Here's the trick. We actually have to maintain this 2 and this 1, and the reason I'm not distributing anything is this. I know that this 2 is equal to this now. And that will go here, because this is also a 2, and this is a 2. So I can substitute it. There's a substitution. So now what I have here is 1 is equal to, we're substituting to the top equation, this is a 3 by the way, is equal to negative 3 minus, okay, and this 2 is now a 26, and don't distribute anything, it's so important that you don't distribute anything, 8, not yet anyway, times all that times negative 2. Now I'm going to go ahead and distribute this negative 2, but I'm not going to multiply it in. I'm going to show you what I'm talking about. It's important you don't multiply it in. So this 1 is equal to negative 3. And then here I have technically a negative 2 times a negative here, right? If we distribute the negative through and the negative 2. So this becomes a positive. So this is really plus. I'm distributing this negative and this negative 2 at the same time. Negative 2 times a negative is positive 2, so it's 2 times this. So it's going to be plus 26 times 2, right? And then 2 times this is going to be minus 3, so it's 2 times 8 is what I'm saying. 2 times 8, which is actually 16. Why am I saying 2 times 8? Because this has gotten multiplied by this first. Negative 2 times negative is positive 2, so positive 2 times 8 is 16, and this is what I have, okay? And this is really, really important because here's the trick here. This is what's going on here. We're maintaining these numbers that we're having, right? Because I'm trying to use these things right here. So what I see here is I have a negative 3, which is really a negative 3 times 1, and a negative 3 times 16. So what I have here, and let me make some space. Let me erase this. Get a bigger eraser maybe. Thank you. Is 1 is equal to, if I have 16 negative 3's and 1 more, this is going to be negative 3 times 17 this time, and then plus 26 times 2. Okay, so really what I have here is I have negative 3, remember this is all mod 26, so this is negative 3 17 times 17 plus 26 times 2 equals 1 mod 26. This is all mod 26. So this is equal to 1 mod 26. So what does this mean? Okay. Well, here's how it works. And if you really should watch 2 or 3 videos I'll post that you should watch on modulus, right? But here's the deal. If this is mod 26, then 26 times anything will just be the same. As long as it's a multiple of 26, it'll be 0 mod 26. So this is really nothing. So here's what I'm trying to find the inverse of. This, if you recall, negative 3 times 1 over 3 would equal 1, right? I'm trying to find this guy. This is your determinant right here. This is your determinant of K. And this is your inverse of that. And this is what I'm trying to find. And now I have it. I'm looking at it right here. This is 17. So technically, this is your determinant, and this right here has to be modded 26 still, but this is your inverse. So what I'm now going to say is, okay, 17 is equal to something times 26 plus r. We're going to mod this thing, make sure it's modded. So sometimes it'll actually change and sometimes it won't, okay? So we'll call it plus r. But here's what I'm saying. I can't go above 17, so basically this will be what? This will be 0. So if this number is actually less than 26, as it is in this case, what this means is it's 0 plus 17 is what 17 is, okay? We're not adding anything to 26 times something, so that means that this right here, 17, is actually congruent to 17 mod 26. It is its own modulus. I mean, it is already modded already, as it turns out. So as it turns out, this right here, this negative 1/3, I should call that, is equal to 17 mod 26. So the way we can write this inverse modded 26 is 17. I'm telling you 17 is the same thing as the inverse. That's the hard part. It took me a while to figure that out, but we got it. So here we go. Now we can find the inverse matrix. It's 1 over the determinant of K, modded 26. I should write that as mod 26 times the adjunct matrix of K. Okay, now what I found here, this 17 is this determinant here, or 1 over this determinant mod 26. That's what this 17 is. That's what this part is right here. Okay, we already have this, the adjunct matrix of K, because we found it up here. We found it a good ways up here, right here. This is what we have. So we're going to take this matrix. I wonder if I can copy that actually. And so we're going to do that. So we're going to multiply this by 17. And this will give you my inverse of the key, inverse matrix of the key. Okay, and this is not the only way to find the inverse of a matrix, but this is the way you would do it to demonstrate that this greatest common divisor of these two things is equal to 1, which has to be true for this to work anyway. Okay, so not that doing this a different way is like a whole lot easier. It's really not, but that's not the only way to do it, of course, to find an inverse matrix. You could use row operations to do that. But let's multiply this through. So we're going to multiply every number here by 17. That's what we're going to do. Okay, so we multiplied all that through. So now I will reduce this mod 26. So this will equal some other matrix. Mod 26, we call it. And how do you reduce this mod 26? Well, it's actually not that hard. Again, this is kind of what we were doing before with the encryption process. What we have this is negative 238. That's what we're going to do. We're going to set that equal to some number times 26. We're going to call it, I don't know what you want to call it Q or something, times 26 plus R. Now, when you have a negative number, the idea here is to make this more negative than that. Okay, just as long as it's a more, okay, and not more than 26 more, but more. Okay, so what I'm telling you is, if I divide this number by 26, what is that going to give me? It gives me so if I divide this number by 26, that's 238, right? So let's get this calculator. If I say 238 divided by 26, what does this give me? It gives me this. So I know if I multiply 9 by 26, it's going to be less than 238. So I'm going to round up. Okay, so it's going to be 10 times 2 times 26. That's going to be 260, right? So here's what I got here. I got negative 238 is equal to, if I round it up to 10, in this case negative 10 times 26, right? That's what I'm looking for, making it more negative. So what I'll have here is negative 260 plus some positive remainder, which is what I'm after. So, so how do I actually make this 238? What do I have to add to 260 to make it 238 is the question, right? And of course that answer will be 22 by the looks of things. Okay, so if I add 22 to this, I'll get that. So this is my remainder. So what I'm going to say is that negative 238 is 22 mod 26 is what we're going to say. This is the process we do. We have to do the same thing with every number. It's different for the positives, though. We're not trying to make a negative number here for the positives. So let's do 187. I'll show you a positive example. In this case, we're just going to multiply some number, q, times 26, as before, plus r. And this time we want this to be less than this number when it's positive. Here we want this to be more. Well, this one should always be less. This number needs to be less than this. This number is more negative, so it's less than negative 238. So this is always, the idea is always to make this less than this number. Even if it's negative, you need to make it more negative to make it less than that number. So here, though, I'm just going to divide 187 by 26. And that's going to be 7.19. So I'm just going to multiply the 7 by 26 right here. I'm going to call this q a 7 times 26 plus r. This is 187. And then if I multiply 7 times 26, what does that actually give me? It gives me 7 times 26 is going to give me 182. So here's the cool thing about this. We're going to have 187 is equal to 182 plus r. So r had to be 5. Huge delay here on my computer, but that's a 5. And I'm going to go through this whole thing and just speed up this video. I'm going to do this process for all these numbers, okay? That's what I have to do. We're almost out of the woods. I know it seems like a lot, but I'm explaining the whole thing. I could have done this calculation much faster, but since I'm explaining it, it's taken the whole thing, encryption and decryption. It's taken about an hour to explain it all, but it's only because I'm explaining it. Actually, doing the calculation should only take about 10 minutes. Okay, so now we have, I went ahead and fast forwarded this through here and made the rest of it, okay? This is the final part. We're going to get our plain text back for the decryption. So the plain text will equal the cipher. So put this in a matrix. It's really a matrix. It's going to equal the cipher matrix or cipher text matrix times the inverse of the key mod 26. Mod 26. Okay, so my ciphertext, if you recall, was 21, 0, and 11. That was my ciphertext, okay? That corresponds to the word val. So we started with. And now that I have this inverse matrix, which is what this part is right here, I'm going to multiply that together, and then mod 26 is the answer, and then it'll give me back the plain text, and that will be decrypted. And that was the whole process. So we're going to multiply this by 22. Okay. So it's the same process as before. We're going to multiply the row against the column, row over the column, and my answer will be a 1 by 3 again. So we're going to do this. And I'm actually not going to bother multiplying the middle one. I'll show what I'm doing. 21 times 22. And then what I'm really going to do is add 0 times 6, which I just know is 0, so it's not going to be any point. 11 times 5 plus 11 times, 15, 11 times 15. And then we do this again, this row over this column, and so forth. So we got this. So we got 21 times 5 plus 0 again, because 0 times 17, 11 times 13. And then lastly, this row against this column. 21 times 1, 0 times 24, which is 0, plus 11 times 1. So when we figure all these numbers out, okay, that will equal these three numbers right here. And now we have to mod 26. So we have to mod 26 these numbers, and this will give me back my plain text part. Okay, so to do that, if you recall, we're going to use this formula. N is equal to Q times the modulus, which is 26, plus R. Okay, so right here, this is my value for N, so it's going to be 627. Q times 26 plus R. The idea for this is to multiply 26 by some value and get a value that's less than 627, but as close to it as I can get. So what I like to do is I like to divide 627 by 26 and just get that integer, just the whole number part of that. So I say 627 divided by 26, and this will give me 24.155. But the integer part of this is the 24. Forget the decimal. So I'll multiply the 24 by the 26. This 24 is my value for Q, is what I'm telling you, okay? So Q times 26 is going to be 624. So I got this, which is 24 times 26 plus R. And 627 is going to equal 624 plus R. And this remainder is going to be a 3. This remainder is going to be a 3. Okay? So what that means is that 627 is the same thing as 3 mod 26. Okay? And we're going to do the same thing for the rest of these. Same process, okay? And then when I'm going to fast forward through that, and I'll just, I'm going to write it all out, but I'll fast forward through that, and then you can see the answer, okay? So I'm going to speed through this. Okay, so I fast forward through that, and I'm going to get 3 for my remainders, 3, 14, and 6. So my plain text matrix will be 3, 14, and 6. And I'm trying to decrypt this message, so I'm just going to look at the alphabet chart and see what 3, 14, and 6 give me. So zip back up here. 3 is a D, 14 is an O, and 6 is a G. So this word is a dog. And that's what I started with, dog. Decrypted. Okay, so thank you for watching. That was really fun to figure out. Hopefully you can do the same.